Hello physics students. So this video is actually a continuation of the last video, but because the topic of the last video was so fascinating, I decided to split off the practical applications and the calculations to a separate video so that the last video could focus only on that beautiful theory. The first thing that I want to add to the last video is that the fact that particles like electrons are actually little waves when they're traveling along through the world, that allows us to actually use electrons in a microscope application. So when you looked in, say, biology class through a traditional microscope, you were using visible light. Obviously, you were looking into the eyepiece, the light was going into your eyes. But that creates a limitation because light is of the order of 10 to the minus 7th meters. Now that allows you to see things very small, but not smaller than that value. For example, a single atom is, like maybe hydrogen, a diameter of 10 to the minus 10th meters. This is much bigger, 1,000 times bigger. Analogy would be like if you put your finger on a tabletop, would you feel a single dust particle under your finger? No, it's too small compared to your finger. But maybe to a bacteria, that dust particle might look like a mountain. So instead of using light, we can use electrons and accelerate them. And as you could see from the de Broglie wavelength that we learned about in the last video, the faster they go, the shorter the wavelength gets. So there's not that limit that we have in the visible light. And as a result, we can see smaller things with the electron microscope. The next thing, a calculation example. So here's something you might encounter maybe on a test. An electron passes through 125 volts, determine its kinetic energy, its speed, and its wavelength. So before I move on, let me create a pause to allow you to copy these notes down. All right, let's move on. So the first thing, we are given the voltage. How do we get kinetic energy? From the basic equation that defines voltage. It's in the reference table. I won't bring the reference table up, but it's in the electricity section. Voltage is work over charge. And remember, work is measured in joules, so any energy quantity can go into that expression. Heat, whatever, potential energy or kinetic energy. So I replace the W with kinetic energy, and so I have V equals KE over W. If I move KE over Q. If I move the charge over to the other side, I have kinetic energy equals charge times voltage. Again, it's an electron, so we could look up its charge. It's not given in the problem, but we could look it up front cover of the reference table. One elementary charge is what it's listed as, 1.6 10 to the minus 19th, and the voltage was given. Multiply those, I have the kinetic energy. Next thing, the problem asks, well, what's the speed? How fast is it going? So we use the expression kinetic energy related to speed, which is in the reference table, mechanics section, the last page of the reference table. We plug in our answer here. The mass of the electron, front cover of the reference table, rest mass of an electron, 9.11 times 10 to the minus 31, and we solve for the speed right there. Very fast, 6 million meters per second. Let me create a pause to allow you to copy these notes down. All right, one last thing. We have to calculate the wavelength. So let me make some room. So this is the basic equation for the wavelength of a particle moving a certain mass, certain speed. So H, Planck's constant, front cover of the reference table. So again, maybe I won't come up to the front cover, to the camera, but basically it's right here where my index finger is on the front cover. So 6.63 times 10 to the minus 34. Again, as I mentioned in a previous video, a lot of students put joules per second. I don't know why. It's joules times second. The mass is, again, the electron. Speed. Punch that on a calculator, and you should get. So, again, remember, light, all of the light in the visible spectrum is of that order. So this is smaller, allows the electron microscope to see smaller sizes. Let me create a pause to allow you to copy these notes down. All right, so that's it. Nice short video. Just again, you need to know that practically, a practical application of matter waves, one of them, besides something we're going to talk about later, but is that these particles can be used, the wavelength can be used as a microscope. So electron microscope is an example. And then you need to be able to do some basic calculations relating voltage and energy, energy and speed and wavelength. Now, if you wanted to design an electron microscope that could measure a certain and produce a certain wavelength, you would do the calculation in reverse. If you knew this, you would plug it in here, solve for V, and maybe you get 6.6. So maybe we wanted this, we plug in, we now know the speed. We go back over here, we plug that in for kinetic energy. We have the kinetic energy, and then we figure out what the voltage is. So we'll do the calculation in reverse, and we could now know what to turn the dial of the volt power supply to generate these electrons for electron microscope. All right, so that's it for today, for this video. I hope you enjoyed the calculations as well, maybe not as much as the theory of the last video, but that's it. I'll see you in the next physics video.